Good afternoon, everybody. Welcome to our pre-lab lecture. I see I have three students online so far. I don't know if some of you are still on the way. Nevertheless, I'll get started. It's now 4 minutes after 1 o'clock, and I don't want to wait any longer. Today experiment is on determination of precipitation reaction. In other words, we will see or look at the criteria by which you can determine whether a precipitate will occur when you mix two reagents using the free Gibbs energy. I know you have covered the chapter on free Gibbs energy. I'll just give you a little bit about, overview on the background for today's lab, and I'll jump some of the concepts you are expected to recall all the way to Chem1. Chem to allow me to share my screen because I will be writing something on my whiteboard. Right now, I do have the whiteboard on my left, and a worked example on the right side of the screen, and below you will see the data sheet. Look, you are able to pull the data sheet. I had to repost it again in PDF format. Can you check if you are able to see and let me know? Look, let me know.
I was able to see it for experiment 11, but I was talking about experiment 10 because I had sent you an email that for experiment 10, like last week, when I go on there, like the file or whatever, the 9th page where the data sheets are supposed to be doesn't show up for me.
Oh, last week. Okay, I'll check again. Let me just get done with this and then I'll come back to that. I'll respond to you.
Okay. Thank you.
All right, thank you. Let's just move forward, and then you can remain after this, and then we can troubleshoot while still you are on here, so that at least you can address that later. So for today, precipitation, all right, precipitation, predicting precipitation reaction using free Gibbs energy. You know these thermodynamic terms. Thermodynamic term, we call these free Gibbs energy, and we are going to use this term to predict when you mix two ions, all right, will the precipitation take place. The equation, before I show you what criteria we are going to use, the equation used for determining this is given by enthalpy of reaction minus temperature times change in free entropy. This is called enthalpy, all right? This is called enthalpy of reaction, or just the heat of reaction, you know what that? And this is given in kilojoules per watt, kilojoules per mole. This is called entropy, or change in entropy, you want to say. This stands for change in entropy, and it stands for, all right, it stands for the dispersion in energy. Sometimes stand for, we define this as molecular randomness or disorder, or simply energy, the energy dispersion. We disperse energy in a system, right? When we talk about this, we are coming in with the system, you know, the surrounding and so forth. So with this, the unit is given in joules per mole. You will see in all general chemistry text, the units are always given in joules. If you look at the table, when you mention about the table, look, I thought you are referring to what I do have on my slide. But nevertheless, let's look at the units for just the units for delta H and the delta H and S. If you look at the entropy, which is molecular randomness, it's given in kilojoules, and this one is given in kilojoules, this one is given in joules. You got to pay attention to that, so that when you use this equation, you don't just add up and say, all right, it is this is what I'll get. No, this is always in kilojoules, so you need to change this to kilojoules before you plug in this equation. And temperature is always in Kelvin, all right? Temperature is in, this is in Kelvin. This temperature in what? Temperature in Kelvin, and you know how to change the temperature in Kelvin? 273, all right, 273 plus, degrees Celsius. You can use 0.15, it's fine, or 273 is fine, okay? So when we plug in the information in there, the numerical value, all right, for change in free Gibbs energy, is the numerical value for this once you plug in. If it is a negative value, and then precipitation will take place. If you end up with a negative value, all right, that stands for negative value, then you make a conclusion that, oh, precipitation will take place. If it is positive, if the value is positive, this means, all right, this means the no PPT, no precipitate. If you plug in this equation right here, then you can make a conclusion whether the precipitation will occur or not, That is, the benchmark. This is the benchmark by which you will be using to make a conclusion whether the precipitation will take place or not. Now, once you determine in this exercise, once you determine that the precipitation will take place, you will have to, all right, you will have to write the chemical formula of the precipitate. And I'm going to walk you through a sample example. We will all work together in trial 1 and see how you will proceed with the calculation. So we have seen, what are we looking for? If it is negative, precipitate will take place. If it is positive, no precipitate will take place, all right? Now, there is, what is meant by this. If I say this now, change in standard, we say this is the standard free Gibbs energy. If I rewrite the equation with this, minus temperature, change in standard state here, this means at STP. You know what that means at STP? That means that concentration or molarity equals to 1.00 molar at STP. Temperature is 298 K, and pressure is 1.00 atm. If we can set this condition to this, what I give you here, we are working at the concentration. 1 molar, you can see behind that, this 1 molar here, if we are working with that, with this pressure at 1 atmosphere and temperature, and then we say that we are at STP, and this equation will hold through, However, when we normally do this exercise, this experiment in the lab, of course, the lab will not be at 1 atmosphere. It's going to be a different pressure other than what you see here. You see that? It's just going to be different from what you see here. And 298, the room temperature varies from, time to time. Maybe in the morning it is slightly cooler than afternoon, and the temperature will change. What you see as concentration, the concentration, look at my cursor key on the bottom left corner of your screen, the concentration of sodium iodide, the concentration of silver nitrate here, they are not at 1 molar, but the concentration you see on the data sheet here, they are all in 0.2 or 0 molar. These are the concentration of all these reagents. Pay attention to that. So the point here is we will not be working at STP, that means standard temperature pressure, and we need to use a different equation other than what I just gave you earlier on. This is for standard state. At non-standard state, all right, at non-standard standard state, we can still determine whether the reaction will take place or not, and that is what we are going to use in completing the data sheet. At non-standard state, we talk about delta G Rx, that means free Gibbs energy of reaction at non-standard state is given by change in free Gibbs energy at standard state, all right, plus ln of Q, and this Q here is reaction quotient, quotient, which is just concentration of the product raised to the coefficient in the Balanced equation M of reagents raised to the concentration of the coefficient in the Balanced equation. Q is the reaction quotient. For delta G naught at standard state, delta G like that is determined by using this equation. Summation of, that sigma means summation, coefficient in the Balanced equation for the product, that means T of naught formation of the product, multiplied by the coefficient, minus summation of N, delta G naught formation of the reagents, reactant, R for reagent, so product minus reagent. In this case, you have to determine this one, the blue. Let me circle the blue right here. You see this equation right here, summation of whatever we have for product, we will use the coefficient in the Balanced equation. For example, here, we will look at this coefficient here is 1, 1, 1. I'm looking at the cursor key. Look at the cursor key on the top left corner on the screen. If this is the equation, the coefficient is 1, 1, 1. So M and N are coefficient in the Balanced equation. Summation. So if we have two products, we will have to find for this, we'll have to find for that, and we will take it from there. This is this equation here. Let me call equation 1 here. We will use in determining this value, this thermodynamic term. Use equation 1. Use equation 1. This is what you will do for that. Ln of, Ln is the natural log. It's a function on the calculator. But Q, you have to, it's based on the Balanced equation of, the thermodynamic equation as it is written. Remember, we are looking at the precipitation, not solubility product, let me give you our equation here to understand what is going on. We talked about last time, remember? Silver chloride, like that. No, it doesn't even want to go. It doesn't even want to go to. Doesn't even want to go to product. So we have a small forward reaction to form Ag ions. Not even before we put concentration of that. Just say it's just gonna form silver plus, all right, silver plus chloride, like that. And this is aqueous, and this is aqueous. This is solubility equilibrium. But for precipitation, it is the opposite. This is what we are trying to determine. If I have silver ion plus silver ion plus chloride ion, like that, this is aqueous. Aqueous. It doesn't want to, it's going backward, forward, doesn't want to come this way. Will this form? The question is, will that form? That is what we are trying to determine, that will two ions form a precipitate if we mix. And we can use this equation at non-standard state, this equation at non-standard state. What I'm trying to show you is how we're going to get this using the product there. If we use this equation, remember in chemical equilibrium, solid do not affect, all right? Solid do not affect the Kc value or equilibrium constant, it's just unit. So here, Q will be 1, which is solid, for solid, 1 is for solid, over concentration of the silver ion times concentration of chloride ion. If we add other coefficient in the balanced equation, and then, you know, we will raise to that coefficient. For example, say hydroxide concentration. This is 3 moles of hydroxide concentration plus 1 mole of iron 3 in, doesn't want to go to solid, so it's going there. For iron 3 hydroxide, let me just put this 3 here, and this is solid, that is solid. So Q for this is aqueous. Q for this will be 1 for solid, iron 3 hydroxide, and hydroxide, what I'm doing with hydroxide is raised to what? It's raised to 3. This is raised to 3. And iron 3 ion is raised to 1, so you don't see that 1. This is how you find Q, and then you say ln of. If I know the values, I'll plug in there and say ln of whatever. I'll just do it separate in order to get this term right here. For non-standard state, to get this term right here, you will use this equation, ln of, you know, whatever the value you will get. Some of the, if you look at the data sheet, some of the reagents, they might not be, you know, 1-to-1, there is 1-to-2 and so forth. You have to know how you will proceed with that. Suppose we have calcium hydroxide. Let me go to 1-to-2, such as 2 moles of hydroxide, all right, aqueous, plus calcium. Will this precipitate? All right, it doesn't want to come towards the left side. This will form calcium hydroxide, and solid. So ln of Q for this will be, or Q, sorry, is 1 for calcium, all right, calcium hydroxide for solid, of hydroxide raised to 2, hydroxide concentration raised to 2 of meantime is calcium ion, calcium ion. We put that. That's how you find the, the Q. All right. So with that, any question on, have you understood the question, this equation? I was just trying to explain this equation in order to say, overall value for delta G at non-standard state, is it positive or negative? If it is positive, all right, if it is positive, and then no precipitate will take place. If it is negative, and then we say precipitation will take place. So let me just be specific. This is at non-standard state. Wherever you see that there is no subscript O, and then we are dealing with non-standard state, We are dealing with non-standard state. Here is an example. Before I walk you through an example, any question on this equation? Any question on this equation right here? This is what we will be using to complete this data sheet. Any question? Delta G is positive, is non-spontaneous. That means it will not form, yes, look, it will not spontaneously form a precipitate. So when we talk about spontaneous or non-spontaneous, maybe I should have said that, use that term here, that it will spontaneously form a precipitate. There will be no spontaneous formation of a precipitate. It's just spontaneous, yes. Positive delta G, non-spontaneous. Negative is the spontaneous precipitation reaction. Meaning as soon as you put them together, it will form a solid. Here are the thermodynamic terms. There is something I want to highlight with this. Let me just enlighten this so that we can see clearly the values. If you look at this example, all right, if you look at this example, if we want to determine whether the precipitate will take place or not at non-standard state, that means we're going to be using this term right here, non-standard state. We have to determine first delta G naught. Remember, this is the equation we are going to use. This is the equation for non-standard state right here. At non-standard state, it is delta G naught plus RT ln of Q, so it should be RT ln of Q right there, where R is the universal gas constant with 8.3, all right, 8.3145 kilojoules. I'll recommend for this use, all right, for this use 8, if you have 0.0081314 kilojoules per mole because of this delta G naught you will have in kilojoules. Look at the top part right here. It is in kilojoules. So if you are calculating delta G naught in kilojoules, you want to make this term plus. You want to make this term to be in kilojoules. So I'll change the R value to kilojoules. And of course, the temperature is 298, and we are working at 125. Now, we will be working with the concentration for the reagent will be 0.2 molar concentration. So you will construct a table that when you mix nitrate and ammonium ion, will the precipitation take place of ammonium nitrate? So first, the thermodynamic terms here we will use to find what? If you are not given, you got to calculate using the equation. But for our case, we don't need to calculate. We don't need to calculate, you know, you don't need to calculate this. I know sometimes you may be required to do this. You may be required to use this equation, all right? Delta G naught minus T delta GS. Or we can also use the one for product, which I gave you earlier on. This is M G naught for product minus N G subscript naught for reactants. This is the equation you will use. Equation 2 is what you will use, unlike what we have here on the diagram. But if you are not given, you have to use equation 1 to determine delta G naught, given this and given that. Of course, it's going to give you delta G naught given right here. This is delta G naught, which is negative. This is not what we are using to determine whether the precipitate will take place. We now have to use delta G naught R. Now, with this, all right, how do we know that, you know, delta G naught will take place? If it is positive or negative, it will take place. But if not, then we include that to say that no reaction or no spontaneous reaction, no spontaneous reaction. Well, there is an example here on how to determine whether, all right, whether a precipitate will take place when you have barium nitrate and calcium, all right, barium nitrate and calcium iodide. In this case, we have, it is assumed that we have here, look, this is what I want you to visualize when you do this exercise. We have 0.2 molar, 0.20 molar barium nitrate, like that, barium nitrate. This is barium nitrate, all right, barium nitrate, and it is aqueous. And we have here barium what, 0.20 molar calcium iodide. All right. Forget about when you mix two, you want to know which precipitate will take place. Calcium, barium nitrate, and calcium iodide. Just the way we have here on the data sheet. Here, there are two solutions, solution 1 and solution 2. Solution 1 and solution 2, let me just bring this up here. You'll see solution 1 and solution 2, sodium nitrate, sodium iodide, silver nitrate, sodium iodide, silver nitrate. So you have this concentration. You don't see on the data sheet this, but it's assumed that all of them will be 0.2 molar to start off with. Now, you will assume that you have mixed the two, all right? Assume that you have mixed the two. In the first one, there is barium nitrate, barium, which is +2, and then nitrate, which is 3 negative, and then calcium, which is what, which is +2, and iodide, which is -1. So if it is double replacement reaction, double replacement reaction, this will combine with that, and this one will be combined with that. The reason why I'm adding the charges here is I'm uncrossing over. You know how to write the ionic charges, uncrossing over. There is a 2 there. You uncross 2 came from barium nitrate, you know. You should be rounded, well-rounded in your polyatomic ions. This will help you in writing down the possible precipitation, possible precipitate. One is barium iodide, or 2, calcium nitrate, and this is the equation for. We don't know which one is our precipitate, and we will use non-standard state to determine whether the reaction will spontaneously, or which one among the two will spontaneously precipitate out, fall out of the solution if we mix these two solution. And remember, we'll also be using 0.2 molar, 0.2 molar. If you look at, before you mix the solution, all right, before you mix the solution, you need to know the concentration of ion. Iodide, calcium here, calcium is 0.2. Iodide is twice, because there's a subscript right here. There's a subscript right there. So 0.4, because I'm multiplying it by 2, and remember this is concentration, molarity, molarity. For this one, barium, concentration of barium, Ba+2, is 0.2 molar, and then nitrate, all right, nitrate is 0.4. That is before you mix. It is good to know that, or you start off with before you mix first. I want you to have the concentration of each ion, all right, before you mix. You see how I have them separate? If the concentration of the entire solution is 0.2, for each ion, since for every 1 mole of this that is in the grid, I have 1 barium ion, and that's going to be respective 0. But if it is twice the 2 nitrate ions, it's going to be twice the value you have there. That's what's happening. Likewise for calcium iodide, that's why I have 0.4. Now, after mixing the two to form, like, you look at the diagram, I have put what? I have put everything in one container. The concentration of each ion will be now a half of what? A half of, all right, will be a half of what you started with. So this is 0.1 molar. This is 0.2 molar. This is 0.1 molar. All right, this is molarity, and this is 0.2 molar. Why am I changing it? You know, it might be confusing. Remember, individually, this was 0.2 and 0.2. In the direction called for taking equal drops. So if I say, we can even pick any. We can even pick any volume, 1 ml plus 1 ml. For this to work, you should mix 2 equal what? 2 equal volumes of each reagent. Therefore, the original concentration will be 1/2. If molarity of a solution is 2 molar, if I double the volume, the concentration will reduced by half. Therefore, each molarity you start with will be 1/2 when you mix, 1/2 when you mix. So even for this one right here, this is 0.2, 0.2. We will come back to this. But for now, this is what is going on. So for the first possible precipitate, it is barium, aqueous plus, all right, iodide. You see iodide, this is 2 iodide like that, all right? To balance the equation, aqueous, this is aqueous, doesn't want to go to, you know, it's lying towards barium iodide like that, barium iodide, and this is solid. Remember our concentration for each when you mix. Remember for concentration when you mix, you don't have to draw this. Once you figure it out how it's going, then you'll be fine. So this is 0.1 molar, and this is 0.2. It is 0.2 molar. After mixing the two, I want you to follow the concentration, how the concentration is changing. Why did we have the original one, the initial one? Why did we have to have this? It's because of doubling the volume. When you double the volume, the concentration will reduce by 1/2. The reason why we want this is to get the ln of Q. Ln of what? Ln of Q. This should be ln, all right? Yeah, I wanted to say ln of Q is given by 1 over the concentration of 0.1 raised to 1. It's just raised to 1 times 0.2 raised to 2. This is what we would need in finding the concentration reaction question. So reaction question for this equation. Remember this equation, delta G naught, delta not G naught, but Rxn like that is given by delta G naught like that plus RT ln of Q, RT ln of Q. We know this, right? I've shown you how to find this. Where are we going to get this one is assumed. Remember I say use 0.008314 because the delta G naught this here will be in kilojoules, right here. How are we going to find for this one, this equation, for this equation right here? For this equation, how do we find this term right here? Remember, it is product minus what? Product minus reagent. Product minus reagent, we're gonna use this equation. Delta G naught is given by the summation of M, delta G naught product minus N, concentration of the, delta G naught reagent for reactant. This equation here, where am I going to get this? There is at the bottom of this handout I have online, all right? I have online, there's a table at the bottom you will have to use. This one right here. Barium, we are looking at barium and iodide. This is where you look at where it formed is barium iodide, and delta G naught for barium iodide is, this is product. Product is given by, you see where I'm looking at barium iodide, negative, this is negative 601.41, remember it's in kilojoules. The coefficient was 1. The coefficient was 1 here for barium iodide, product minus reagent. Now, this is where you have now to say minus, all right, we have to find the summation of these two, barium and iodide. This is where you just come and zero in for barium. You see barium right here? This is for barium alone, formation of barium ion. And then for iodide, this is for iodide alone at the top. For an ion, anions negatively charged. So I'll just have here and say 2, all right? 2 times for iodide is 51.57. Because I have two iodides ion here, 2 iodides. So I multiply by 2 this value. Plus, all right, summation. For barium, it's by itself, so this is a negative. You have to maintain the, look at the sign, this is negative 560, 560, all right, 560.77, and you plug it in your equation. This will give you delta G known for the reaction, which you will plug in here. You're gonna plug in this equation right here. You'll plug in this equation. If you end up with a positive value, you say that this one will not spontaneously form. Or if it is negative, it will spontaneously form. If it is positive, it will not. If it is negative, yes, it is. So you'll do the same thing for what? You'll do the same thing for calcium nitrate. So initially, this is, you say, possible precipitate 1, I'm gonna write it down here. It doesn't really matter which one, so long as you label out your 1 and 1 respectively. And then you're gonna calculate delta G naught using this equation, using the same equation I use here. All right, the equation you see here, you'll make use of this table to calculate for each of the ion. And then the value now is what you will get from this setup. From this setup right here, I'll say the delta G naught for each possible precipitate will come here. If it is precipitate 2, it's gonna come here, so long as I label the names of that. Then delta G naught reaction, you're gonna just put it in here. If there is no reaction, you're just gonna write no reaction. Delta G naught reaction is the values you put here. If you end up with both positive, something is wrong, you got to step back and check. If both of them are negative, something is wrong, you got to go back. One of them should tell you that a precipitate is formed, and you got to write the formula for that. If there is no reaction, sometimes you end up, it's okay. Let me take my statement, because in this exercise, I don't want you to get confused and say, why am I getting negative? If you get negative, that's fine. No. Positive, positive, that means there is no precipitate. All right. All right. So that's what you like. Either no reaction, that means all of them will be positive. There is 1 or 2. It's okay. No reaction. Any question, or we use one example right here to show you? I want somebody to pick up from, let me just assume everything on the screen, and somebody will pick one example on the data sheet I will solve. You will see how we will make use of this table, and you will see how we will complete this, one of the experiment right here. There are 6 of them. We'll solve one, and you will see how to do that. Let me zoom or blow up this, and then you will pick up one. Somebody to write on the chat feature which one you want me use as an example. And we're gonna solve all the way to the end. By the time I minimize this, somebody should have picked one, and whoever will be at the top, I'll call by the first somebody to respond. Fast come, fast serve. 2 seconds. Let me just minimize this right here. Let me minimize this and see my chat window. Did somebody respond? Oh, Ni and what? Look, you pick Ni. Ni, there is Ni and, you know, sodium iodide reacting with what? Is it silver nitrate, barium chloride? You see, Ni means a lot of, you know, a lot of second reagent. That means you are giving me one reagent. If I look at this, you are giving me one vial. So you are saying that take, oh, a nitrate. All right, sodium nitrate, which is, let me see where it is. Sodium nitrate, where is sodium nitrate? Na. I'm trying to look at which one do you have that you pick right here. I don't see anything sodium iodide and sodium nitrate. I wanted you to pick from combination from me. I'm trying to locate where you pick these two right here, sodium iodide and sodium nitrate. The reason why even it's not here, oh yeah, the reason why, you know, like it's sodium and sodium, you are using the same cation. We should have different cation. Okay, I got now. You meant silver nitrate, which is the first one. I see now it's the first one. All right, this is how we're going to proceed with that. And have your calculator, please. So at the outset, you are saying we have 0.2 molar sodium iodide and 0.2 molar silver nitrate. In this, concentration for sodium in this is 0.2 molar. Concentration of iodide, and remember to write ion, is 0.2 molar. It is 1-to-1. I don't see any subscript. You got to be careful when dealing with the subscript. Let me just remove my chat feature. I don't want to give it away. And for this, second reagent, silver ion concentration for silver ion, this is 0.2 molar, and 0.2, I mean to say nitrate. This is 0.2 molar. We are mixing together in a 1 big container. You assume that you are mixing in 1 big container, and the first reagent is sodium and iodide. Second reagent is silver and nitrate. This is double replacement reaction, by the way, and this is negative. So that, look at where we are starting from and where we are moving. After mixing the two in one, equal volume, whether you have 5 ml, 5 ml, or 2 ml, 2 ml, or 3 drops, 3 drops, it should be equal. The concentration will be 1/2. So for sodium, concentration will be 0.1 molar when you mix, and this is 0.1 molar. This is 0.1 molar, and this is 0.1 molar. When you mix, the concentration will be 1/2. If there was a subscript here, please know how to play around with that. It's gonna be twice. If there was a subscript, it's gonna be twice. I showed you that. So for double replacement reaction, silver will combine with iodide, and sodium will combine with nitrate. So let's say, all right, let's say possible right here on, look, possible precipitate number 1. Let's say number 1 there is sodium, all right, nitrate. If this is possible nitrate, and number 2 here is silver iodide. We don't know which one is which. Remember to write the correct, and remember we're gonna write solid. It's a precipitate, possible precipitate. So it's got to be solid. Even though you don't see it here, they are solid. These are aqueous. They're solution, dissolved in water. That's why I'm giving concentration. So if you look at my whiteboard here, if you look at my whiteboard here, right? In order to calculate the delta G naught for my precipitate number 1 here, I will do this. Delta G naught formation for NaI, silver nitrate. It is silver nitrate, not silver iodide. Silver nitrate, like that. All right. I'll use this equation delta G if it's being formed. If it's being formed, we are saying that Na positive aqueous plus NO3 aqueous nitrate to form, all right, to form NaNO3 solid. Remember, it's a precipitate. You have to force it to make it a precipitate. We don't know at this time. We are forcing it to make a precipitate. And remember, the concentration here is 0.1 molar and 0.1 molar. It just changed from the initial what you started with. Remember, in all these exercises here, this is 0.1, 0.1, 0.2, 0.2, 0.2, 0.2, 0.2, 0.2. When you mix, you know what will happen with the concentration. Now, delta G naught for this formation is given by the summation of the M product minus summation of N G reactor. So this is what I'll do, and have your calculator, please. Have your calculator. I do have mine here. So for silver nitrate, which will be number 1. Remember, we had labeled this as our possible number 1. You have to be consistent throughout. This was number 1. You will use this table right here, table 1, and the product here is sodium nitrate. So you look at where sodium combined with nitrate. I'll just follow all the way to the intersection between nitrate and sodium, and this is negative what? Negative 367.00. All right. Minus, if I look at nitrate, for nitrate alone, you look at negative what? That is negative 111 point what? 0.34 plus sodium alone here is negative what? Negative 261 point what? 0.91. So I'm just gonna add the 2 there. It's gonna be what? Negative 111.34 plus 261.91. And I see this is telling me negative 367.00 minus, all right, minus what? 373.25. Remember, from the 3rd grade maths, positive and positive, this will change to negative. This is the same as 367.00 plus what? 373.25. So I'm just subtracting what? Subtracting 367. And I'm just gonna put that as this is positive 6.25. This is kilojoules. This will be your what? This will be your delta G naught for the first reagent, first possible precipitate. And then for number 2, remember this is what we did for number 1. We are done with delta G naught for that. Delta G naught for this, we do the same thing for that. All right, we say number 2, which is AGI. Remember, it's solid. It's coming from AG aqueous plus iodide aqueous going to AG. We are making it solid. Everything product side is solid because of precipitation. From our initial, when we mix the concentration change to 0.1 molar, the concentration change to 0.1 molar, we're gonna need this for reaction quotient. So if I want to find the delta G naught for this, mention for that, it is M, all right, G product minus G naught product minus what? Summation of N, G naught, this is the G naught reagent, R for reagent. Since the coefficient is 1 to 1 to 1 to 1, I look at the intersection between silver ion and iodide ion, and I see it is negative 66.19. This is the product minus for the reactant side. Iodide alone is negative 51. You see iodide? It is negative 51.57. All right, plus, in its summation, negative for silver ion, it is positive, no, plus 77.11. So let me see the product side. It is 77.11 minus 51.557, and I see 25. So this will be negative 66.19 plus, all right, no, minus here. This is minus. Everything in parentheses turned out to be 25.54. It turned out to be what? To be 25.54. That's everything on the product side. So everything will be negative. So this is plus 66.19, and turns out that this is what? This is negative 91.73. This is not. This is delta G naught. This is not what we use to determine whether the reaction will spontaneously form. This is delta G naught. Once you figure it out, remember, you have to be consistent. You cannot just label this as 1 and then you just come and switch the lanes here. No, it should be consistent throughout the end. So I'm just gonna put this right here on number 2. Right here on number 2. Doesn't really matter if you call the other one, no. So long as you label and be consistent throughout, that's fine. So once you know this is what you will now use for delta G naught. For delta G naught at non-standard state, it will be delta G naught formation for that plus RT ln of what? Ln of Q, ln of Q. This is the equation we will use to fill in this column right here. For number one, which was what? Sodium nitrate solid, all right? Sodium nitrate solid, delta G naught, all right, should have just use this right here, all right, delta G naught reaction, not G naught, but delta G is given by delta G naught plus, this is superscript RT ln of Q. Now, this was, you have to go back and say, for nitrate, this was positive. sodium nitrate, that was positive. For this, that was number 1. So I'm just gonna put positive what? Positive 6.25. Remember, they are in kilojoules. And I'm gonna add, remember to use kilojoules for R, 831. You will use what? Temperature is 298 times 298. We assume we are working at, room temperature, 25 degrees Celsius. Use 298, that's what we will be using throughout. This is the temperature we're gonna be using throughout, 298. All right, everybody will use 298. ln of Q now, natural log of 1 over, remember why I had to write this equation before for precipitation. That is why I had to include the concentration. Remember, for product, solid is always 1, and the coefficient is 1 to 1. This will just be 0.1 times 0.1, 0.1 plus 0.1. So 1, all right, 1 divided by 0.1 times 0.1. That's what I get that. And then ln of what? ln of 100. ln of the answer there is, I get 4.605. Once I did the ln of 100, is it ln of 100? Times 298, all right, times 0.008. This is 2, not 3. I meant to say this is 2. 1, that is the universal Cass constant. And I have 11.2, so I'm just gonna add here plus 6, plus 6.25. And I have 17.51 kilojoules, everything including, delta G naught. This will be the value I'm gonna put right here. I'll put it right here. Then I do the same thing for what? Do the same thing for number 2, that is silver. For number 2, that is silver what? Silver iodide, solid. Delta G Rxn at non-standard state is given by delta G naught minus, plus RT ln of kilo, which is what? This was right here. Delta G naught, it is negative 91.73. So here, negative 91.73 is in kilojoules, plus, all right, 0.00821 times 298 times ln of 100. ln of 100 was ln of 100, which was 4.18. So if I do that, that means ln of what? ln of 100, you can say that, times 298 times 0.00821. I have 11, so minus 91.73, and I end up with negative 80.46 kilojoules. This is the free keeps energy at non-standard state for silver iodide. And from what I mentioned earlier on at the beginning of the lecture session, I had to, give you the criteria, the benchmark. So the only one which gives me positive or which tells me it's gonna precipitate is silver nitrate, is negative. And what I'll write here is the chemical formula. The chemical formula for my precipitate is silver iodide, AgI, and you are done with that. Suppose I end up with the part positive, and then I'll write NR. That is what you will be using. Don't worry about how much you're gonna mix for each one of them. Remember, the key thing here is you are working with 0.2 molar of each reagent here, 0.2 molar of each reagent, which will help you in figuring out the concentration in this precipitation, concentration in the precipitation right here. In predicting the precipitation right here, it started with 0.2 molar, 0.2 molar. That's all what you'll have to do for this exercise. I've walked you through, if you're making notes, I walked you through on how to, how to complete a table. If you pay attention, I had a couple of calculations. I want you to attach the calculation, don't throw it away. Use scratch papers, take snapshot and number it that this is experiment number 1, number 2, number 3, number 4, number 5, and 6. I have 6 of them. Look here. This is 1, 2, 3, 4, 5, 6, 7, 8. Oh, there are 8. I forgot about that. If there are 8. And the blue gray shaded area, these are the reagents where you have 0.2, 0.2, 0.2, 0.2, 0.2. And here are the possible precipitate. It's already pre-filled for you. It's the double replacement reaction. Silver is combined with iodide, all right? Yours is to do the calculation based on the table. I do have the table attached. You'll find that online. Any question? Any question? Any question? No question. If there is no question, I will stop sharing my screen. And I think, look, you had a question on last week work. Let me stop my screen and all right. What was the question again? Oh yeah, no question. If there is no question, thank you, and then I'll see you next week. Then thank you.
I do have one last question though, real quick. Do we have a final for this class? Is there like a
no final for this class. It's just the data sheet. We have no exam or nothing like that.
Okay, I just wanted to ask because I wasn't sure. Okay.
All right, thank you. All right, the class is dismissed. I'll see you next week. Thank you.